Welcome to this fourth day of webinar. I will give you a brief recap of what we have done in the previous days. So in the first day, we have seen how to model reinforced concrete shear walls using shell elements and a plane stress material for concrete, and rebars modeled as smeared rebars, so with the plate rebar layer. In the second day, instead, we have seen how to do the same thing, but with the continuum 3D models using a three-dimensional material model for concrete. And this time, the rebar were modeled with fiber beam elements embedded inside the solid domain. Yesterday, instead, we have seen how to use the cyclic truss model and a brief introduction to the beam truss model. And today we will see instead the classes of multiple vertical line elements and SFI multiple vertical line elements. Today we will have our special guest, which is Professor Kristijan Kolozvari, developer of this class of elements. We will start by with him giving an introduction on the theory and the background of this element, and then I will show you how we decided to implement it inside STKO. So how can you practically use it inside STKO and how you can post-process it. Okay, so I will stop sharing my screen, and please, Professor Kolozvari, stage is yours, and thank you for joining.
Thank you very much. Thank you for the invitation. Give me just 1 second to share screen. All right, so welcome everyone, and my name is Kristijan Kolozvari. I'm associate professor at Cal State Fullerton. Happy to be here today and talk about these multiple vertical line element models that's been implemented in OpenSees, and now they're available also in STKO. At the beginning, I just want to acknowledge and thank to all my academic colleagues and students who worked on development of all these models. The models that we have right now wouldn't be possible without work of John Wallace, Kutai Rakchel, Leo Massone, and as well as the students that are listed here who helped me develop this last batch of models, the 3D models as well. So we're going to talk about the two-dimensional models that were implemented back in 2016. And then I'm going to talk also about three-dimensional models. I'm going to describe these models a little bit, show some validation results, and that would be it. So basically, let's just start from the beginning. This MVLEM model and concept is known for a very long time now, I think back from the 80s. So it's not something that I came up with. Like, a lot of people use them. They have their own implementations of it. And back in 2016, I believe, or 2015 actually, we published this peer report with John Wallace and Kutai Rakchel, where we implemented these models into OpenSees for the first time. As a part of that implementation, we implemented the multiple vertical line element model and the shear flexure interaction version of that model, and as well as the fixed strut angle model, which is the material model for reinforced concrete, as well as uniaxial materials, concrete and steel. So this was like a package that was added to OpenSees, again, back in 2015. This peer report is available, and as well as we have a paper in one of the journals, Computers and Structures, that explains implementation of all of these models into OpenSees. So a little bit about the theoretical background about these models. First, start with the simplest one, the basic one where everything started from. It's called the MVLEM, or which stands for the multiple vertical line element model. Basically, this model is just like a fiber model for reinforced concrete wall. This original version had 2 nodes, so it was like a beam column element. We had basically these vertical fibers that are used to represent flexural behavior, and then you have the shear spring here that's used for the shear behavior. So you would have basically, you discretize your wall into a number of fibers like this, and each of these vertical ones you have to assign, or their behavior is governed with the uniaxial materials for steel and concrete. And for the shear spring, you can assign different types of force deformation relationships It can be linear elastic, it can be nonlinear. It's up to the user to decide on that. And this is basically the formulation. So it's pretty simple. That's a nice thing about these models. I mean, they're not perfect. They're macroscopic models. So as opposed to some of the models you guys heard in the past, a few presentations in this session, some of these other models were finite element models. These are macroscopic models and they have limitations. But the good thing about them is that they're very computationally stable and efficient, and they provide reasonably, good estimate of the responses of reinforced concrete walls. This is basically the formulation. Here we have validation of one of these models against this specimen RW2. Again, this is just a two-dimensional model. So in this case, we're just validating against the planar wall. And you can see that the model can do a pretty nice job in predicting the force deformation relationship. If we look at the strain results, again, the model has plane section assumption implemented at top of the bottom of the element. So, the strains can only be predicted as a straight line along the length of the model. But in most of the cases, that's good enough, especially when we're talking about engineering applications. So this is the multiple vertical line element model. One thing that is important to mention about this model is that the behavior of these vertical fibers that represent the flexure and the behavior of this shear spring that represents the shear behavior are totally uncoupled. So they don't have any interaction. So because of that, basically the model and shear and flexure responses are totally uncoupled. So you have to kind of be aware that this model is suitable for flexure controlled walls. If you have wall that has some kind of shear flexure interaction, or it's a shear controlled walls, this is not the right model to be used for that. But for flexure controlled, is working really well, as we saw in this previous couple of slides of validation. So here we have an example when this model doesn't work that well. For example, we have this one specimen that was medium rise. It was aspect ratio 1.5, and it had a lot of nonlinear shear deformations. So if you want to capture a response of something like this, you will see that you can get very different results depending on what type of response or what type of behavior you implement at this shear spring. If you implement a linear elastic shear behavior, then you can overestimate capacity by quite a bit. You can then implement like a nonlinear shear behavior with some shear capacity if you decide to use the nominal capacity of the wall or the shear that corresponds to the moment capacity. You see, you can get different responses. So that's one thing someone should be aware of when using this model. What are their limitations? Here we can see actually the just response of this shear spring. And again, this will be the experimental data that just shows load versus shear deformation. This is the linear elastic shear spring we're using. Obviously not that good of a choice. If we're using some kind of nonlinear shear spring, then you can get closer. But again, keep in mind that shear and flexure are uncoupled. And what that really means, we can see here in this conceptual kind of figure. And this really stands for every fiber model with elastoplastic shear behavior that has uncoupled flexure and shear responses. At the beginning, both of these shear and flexure deformations sort of happen together and they evolve together as we push the wall laterally. But then once you reach the shear capacity of your shear spring, at that point, you're just going to be sliding, along this shear deformations, and you're going to have kind of a sliding shear deformations, and flexure will be stuck where it is at the point of shear yielding. So that's the limitation of these models, the MVLEM, as well as any other fiber model with uncoupled flexure and shear behavior. Again, they're good for slender walls, for flexure control walls, they're great, but when it comes to moderate or squat walls, they have these limitations. So this was the motivation to develop something better that basically will improve this and to develop the shear flexure interaction version of this model. So that was the next objective in our research. And basically the way we did that, well, we sort of took a step forward from this original MVLEM concept, and we replaced each one of these uniaxial fibers, like this is uniaxial strain and stress, right, with the biaxial material. This biaxial material is basically has the ability, it's like a plane stress type of behavior. It represents reinforced concrete. So it has both materials, steel and concrete, within one material behavior. And it couples at this fiber level, you know, it couples the axial and shear strains and stresses, right? So through that axial and shear coupling at the fiber level, we actually are able to capture the coupling between flexure and shear at the whole element level. And that's really the key of this SFI model. So particularly in OpenSees, we implemented this fixed strut angle model as this reinforced concrete panel behavior, which is, again, also available as an ND material. So this ND material, just one slide about that. It's a fairly complex material model. It has many layers to it. It has a part that represents concrete behavior. It has part that represents steel behavior. It has also some mechanisms that representing transfer of shear stresses along concrete cracks, as well as the reinforcement dowel action. Again, relatively complex model. It has three different stages of behavior: uncracked, first crack, and second crack formation. There's an assumption that the cracks are perpendicular, and that's kind of a simplifying assumption that we are implementing in this. But other than that, it works pretty well. As you can see here on the next slide, there is a validation of this fixed strut angle model against panel test results, where the shear strains or shear deformations are imposed on this panel. And you can see that the responses for the normal strains as well as principal angles are pretty good comparing to the test results. So even though conceptually relatively simple, implementation may be a little bit more difficult, at the end it works pretty well. I have to mention that there is an improved version of this fixed strut angle model that's not available in OpenSees yet, but we're hoping to put it out there in the next year or so. So here, going back to the shear flexion interaction MVLEM model, here we see the validation of this model against that same specimen that we looked at earlier, where MVLEM couldn't really predict results very well. Here you can see that this model captures the response pretty well in terms of the capacity and the cyclic behavior, and also captures the nonlinear shear as well as the flexural deformations. And you can see how they're coupled between shear and flexure deformation, because we can see that the force when we have the shear yielding and flexure yielding is about the same force. So that means that these nonlinear shear and flexure deformations occur at about the same level of lateral loading. And again, just a reminder, if you want to use any of the uncoupled models, you would be really able to do only something like this. So this is an important, I would say, modeling behavior when you're, in terms of estimating the response of buildings. Like sometimes, even if you have a slender wall or a coupled core wall, in a tall building, for example, even though the wall is relatively slender due to higher mode effects, you can have different deformation modes where you can actually trigger the moment to shear ratio, where you would actually start having nonlinear shear deformations. And we spent, I would say, some time comparing these models. There are various papers out there. And one thing that we're also working on is looking at how does this impact prediction of tall building responses using this uncoupled or coupled model. So this is what has been done back in 2016. These are the models that have been available in OpenSees for a while now. And they've been widely used. I've been contacted quite often by many students and researchers, and I'm quite happy about that. But there had an important pitfall or limitation. They were only two-dimensional models, which means that you can really only model the planar walls or any kind of planar elements, and they're pretty much beam column elements. So if you want to model any kind of three-dimensional system with any kind of a line element, typically what people do, then they have to provide some embedded beams in order to connect the coupling beams and things like that. So this is kind of macroscopic modeling with the line models in 3D. So we wanted to overcome these issues. We wanted to extend these models that are available to three-dimensional models, and not only to be the 3D, but also to allow modeling of complex, systems like this much easier. So that was motivation for development of this three-dimensional MVLEM as well as the SFI-MVLEM models. So we started from what we had, but then we upgraded that and we added another two into OpenSees domain, and they were added, I believe, last year, somewhere in March or early last year. So these three-dimensional MVLEM models are available now in OpenSees for some time. And they're starting to being used, and I'm happy to see that also they're implemented now in STKO. Now, as you will see, these models allow three-dimensional analysis. They allow us also to model complex wall geometries. You don't have to have any kind of embedded beams. The beams are already embedded in the formulation of these models, and you can really model the full buildings finally, using these models. So what was this extension really involved? Well, conceptually, it was really simple. I mean, we didn't really change formulation of the actual model itself. All we did here is we basically transformed and had geometric transformation that converted two-node elements to a four-node element. In order to do that, we have some kind of internal beam embedded into the model. Basically, that was basically going from the two-dimensional model from two nodes to four nodes. And on top of that, we added elastic out-of-plane behavior to be able to model the full 3D systems. The elastic out-of-plane behavior is just there to provide some stiffness for the out-of-plane. And this is sort of similar to what you have in other softwares like Perform 3D or something like that. Again, the aim here was really to have a model that would be very practical. So here's a paper that was actually published. I forgot to update this, and it's available in Engineering Structures. It's in 2022 reference, and you can read more details about that paper over there. Here is the OpenSees input. I believe that input in STKO is the same or very similar. Besides a tag and the four nodes that have to be defined in the clockwise direction, you have to define the number of fibers, the arrays of thicknesses, widths, reinforcing ratios, and material tags for those fibers. This parameter C is just the location of the shear spring, which recommended to be 0.4 by some previous research, and so forth. So you can read what it is. It's pretty standard input. It's essentially the same as for the two-dimensional models with some minor changes because now we have a four-node element. When it comes to shear flexion interaction, multiple vertical line 3D model, we also have done basically the same thing. We extended it from 2D, from two-node to four-node, and then to 3D by adding the out-of-plane elastic behavior. So it's a 24 degree of freedom four-node element, which allows the full 3D analysis. And again, you have, here is the input. Besides the nodes and thicknesses and widths of each fiber, you have to provide material tags of the fixed strut angle of FSAM material that you're assigning to each the fibers. And we have this C parameter again, and we have T modification is just basically a factor that you use to modify the out-of-plane stiffness. Default is 0.63 because that represents 25% of the uncracked stiffness, which is something that's recommended in many different practical applications for nonlinear analysis. So it's like a cracked out-of-plane stiffness, but you can use one, you can use very small number if you like, and then the Poisson ratios. This is the input. So let's look at some validation studies real quick here. Because these are 3D models, we wanted to validate them against tests that were subjected to three-dimensional loading patterns, as well as not only planar walls, but like C-shaped wall like this one, for example. So we looked at the studies by Catherine Bayer and her student Konstantin, and they were basically testing 4 different wall specimens They were loaded in all these different directions, as you can see down here, and that was perfect for the validation of these models. This is how we discretized the model. We calibrated materials, and basically each flange or a web was represented by one element. There's no need to have multiple elements along the straight line because they're going to impose plane section assumption no matter what. So you can have only one element along each web or a flange. And here you can see the fiber discretization. So it's nothing too crazy refined, but also it captures all the locations of the confined and unconfined concrete and so forth. Here is the loading patterns. It was actually not very easy to apply these loading patterns. These walls were tested in such a way that the torsion was prevented. So they were only translating without twisting. So applying these loading patterns and having those boundary conditions was a little bit of a challenge to figure out how to do that correctly. But at the end, we managed to match, you know, basically the history that was imposed in the test, as you can see here. Here's just a comparison between analysis times and convergence for the MVLEM and SFI. And as you can see, MVLEM is really fast. It's about 1.5 minutes for this whole analysis. It has about 12,000 analysis steps, and it converges with very high rate of convergence in the sense that you're not going to have to, you know, if you start with the Newton, for example, it's not going to try to go to any alternative convergence or solution strategy. Whereas for the SFI-MVLEM, it's a little bit less, but the runtime is significantly increased here, as you can see, because it's a much more complicated model. So this added, sophistication of the model is costly in terms of the runtime, so something to keep in mind. When we're looking at the overall responses, here we see the responses in east-west, north-south, and diagonal directions. We can see slightly better response, especially in diagonal direction for the shear flex interaction model. But I mean, I would say overall, they're all reasonable. One thing you can notice here is that in the diagonal direction, both of these models tend to overestimate capacity by maybe 20% at most in the worst case scenario. And the reason for this is that we have the plane sections assumption implemented in the formulation of these models. And I will show you later how that really looks like at the strain response level. But that's basically the reason why we cannot really predict that accurately capacity in these diagonal directions. In the principal directions is pretty good, but when it comes to loading the wall in the diagonal direction, there is this pitfall. And really it comes from the formulation of the model. So if you want to get better predictions of capacity in these diagonal loading directions, you would have to use some kind of finite element model that captures better strain distributions at the base. So we actually, in one of the papers showing this, but here I didn't want to get into all that. For the TUC, which is a different specimen that is loaded primarily in the loading directions, kind of the similar issue. And this overestimation is particularly noticeable at larger displacement levels. Here we're looking at the strain predictions for using these two models. Strains are difficult to predict. If any of participants here today worked in modeling of reinforced concrete elements, you would probably know that getting strains accurately in concrete is not a trivial task. So overall, we're actually, quite happy with these results given the fact that these are macroscopic models and they have clearly some, limitations, but overall they are, I would say, reasonably well predicted. In terms of the compression strains, by the way, the test results were measured at both sides of the wall, inner side and outer side. As you can see, these gray and black lines, and the model is only at the center line. So we're kind of trying to really have this red line to be in between the gray and the black line. So that means that the results are good. So compression strains are pretty good. Tension strains may be slightly overestimated. And the same stands for both models. I would say there's not much difference between the two models here. And this is the interesting plot. So here, for example, we're looking at the strains, vertical strains at the base of the wall here where it's shown. And you can see that in the principal direction, sorry, my mouse is kind of bugging here. The predictions is pretty good, but then when we move to these diagonal loading directions, you can see how the strains are overestimated. And the reason is clearly now, it's clear from these plots, is the plane sections assumption of, that is imposed at the base of these, in the formulation of these models. You can see that the results from the tests are, as you yield the wall more, right, as you have more nonlinearity, they're becoming more and more nonlinear, but our model can only do plane sections. So that's basically the primary reason for why we have that overestimation of the capacity, is because of this. Now, when we're having the shear Flexure interaction model, you can see, for example, let's just look at this position E over here, how different the strains are. And the reason that the shear Flexure interaction model has much less flexural strains, now these are the vertical strains comparing to the MVLEM, is because this model also allows nonlinear shear deformations, whereas this one doesn't, right? In this case, we modeled shear as a linear elastic. So for the MVLEM model, all the strains are just flexural, right? So we have a lot of flexural strains. But over here, some of the deformation also comes from the shear, basically shearing the element, and then you have less flexural deformations. I'm getting here a little bit into the weeds, but trying to explain really how these models work. And one interesting thing that you can actually do with the shear Flexure interaction model is these results over here. What this is really comparing, on the right side, we have the shear stresses that are resulted at the base of the wall. On the left side, we have the same strain distributions. And what these results are showing is that the shear stress is only resisted at the fibers where you have axial compression, right? If the fiber is in tension, that fiber is not going to resist any shear stresses. And this is actually something that's realistic in reality, right? You would open the cracks in concrete, and when the cracks are open at those locations, you will not be able to transfer shear. So this shear Flexure interaction model really, these results demonstrate that we do have real interaction between flexure and shear responses at the element behavior. And this is important in analysis, because if you have, let's say, a core wall or a C-shaped wall like this, then the distribution of shear demand and different web or a flange will really be impacted by how much tension or compression you have in those parts of the wall. If you have a, let's say, model with uncoupled shear behavior from flexure, like if you're using Perform 3D shear wall element or even the MVLEM, you know, this shear demand will be kind of averaged out throughout the cross section, and you would maybe, you know, underestimate or overestimate the amount of shear force that goes into the web or a flange of a wall, especially when you have this multi-directional loading. So again, these results really demonstrate this, the axial shear coupling at the fiber level of this element. Here we are just comparing the contributions of flexural deformations. So we can separate the total deformation in the flexural and shear, right? And here we're looking only at the flexure, comparing with the tests. And again, this is something that is very detailed, kind of fine response of the wall. And the way these are calculated from the tests as well is not always 100% accurate. But we can see that in these diagonal and in the web especially, the results are really, really good. On the flanges, maybe a little bit less accurate, but still within the reasonable kind of range of accuracy. Here, I just wanted to demonstrate, you know, the cracking pattern that you can predict with these shear Flexure interaction models. So basically, you know, with a little bit of effort, I'm sure I'm excited to see what STKO post-processing looks like. But I'm sure you can do something like this, where you can actually, right, visualize the cracks. And then we ultimately compared those cracks with the one from the test. And again, you know, this seems to be like a reasonable match in terms of distribution and orientation of the cracks in the wall. And finally, I just want to point out again, I think this slide shows a nice difference between the two models to understand really how they work. I was trying to, increase the scale factor of the deformed shape by the factor of 10 here. You can see that for the MVLEM model, because the flexure and shear are uncoupled, and in this case, we're using elastic shear behavior. So all deformation comes from the flexure. It's kind of, you can see how the wall yields here at the base, and the rest of it is pretty much straight line. When we're talking about shear flexure interaction model, you can see how the wall has this shear, deformations along the height, and on top of the flexure yielding, you also have that other mode of deformation. So I think this is kind of a nice illustration for the same level of lateral displacement. Essentially, different types of strains are being generated within this model. So in summary, these two models are macroscopic. Having that said, they have their limitations, but if you know what these models are can be used for accurately, then they can be very useful. They are computationally pretty efficient and stable. And I'm happy to see that they're implemented in STKO. I'm excited to see the rest of this meeting today. How does that look like? If you have any questions about application of these models, feel free to reach out to me. This is my email address down here. And that is pretty much all I have for today. So thank you very much. Thank you,
Kristijan. Thank you very much for your interesting presentation. Actually, it was very, very useful for me because I've never used the multiple vertical line element before. So I tried to implement it as a programmer. So I went into the code, I tried to understand what the inputs are, but actually this was very interesting for me. In fact, I have some questions for you, but I will ask questions meanwhile I show the implementation in STKO. Okay, so thank you very much.
Of course.
Okay, so let's go now. I will share my screen. And by the way, when I talk about implementation in STKO, it means that how we interface with OpenSees, because there is not a separate implementation in STKO, of course. The solver is always OpenSees. The element is the one that Prof has explained.
Right.
In STKO, we have a graphical interface to it for pre-processing and post-processing. Also, Kristijan, if you remember, as I told you, I made a couple of slight modifications in the set response method. I will show it to you because if it looks fine for you now during the presentation, I will do the pull request by tomorrow. Okay, so that it will be easier to discuss on the pull request if I show you something now. That's why I decided not to do the pull request before. Okay, so I go back here to the presentation just to just to give you a recap, Kristijan, in all the previous versions, all the previous days, we have just picked the same example, and we were using the same example for all the models, which was basically the Mastianek wall, which is a very squat wall. Actually, the aspect ratio is 1:1. Then looking into some of the papers, so I tried to model this one also with the SFI-MVLEM. In one of your papers, I've seen that there might be problems with a very squat wall, and
right.
that you were developing this one. Actually, I've seen this one just today, so I will show you. But is this one something a lot different from the SFI-MVLEM? I've seen the SQ, which was suitable for squat walls, right?
This is one of the versions we had. Actually, we kind of left this one behind, but we have a version with Leo Massone and his student that works better for squat walls. And currently we're writing a paper about that. So then once we publish the paper, in the next, I would say, year or so, I will implement this model as well, and that will work better. The MVLEM and SFI-MVLEM are good up to maybe 1.5 aspect ratio, maybe 1. But it's more for like medium rise and slender walls, not for very squat walls. Again, we have models for that, but they're not available in OpenSees yet. So I'm hoping to get it done sometime soon.
Okay. So actually now we start showing how it performs with this one, because in any case it performs pretty well. Of course, it cannot represent a perfect diagonal crack here because you need deformation here, while the line cannot remain plane, but the overall response seems fine. And then I will show you the same example you were showing there, the TUB, I think it was.
Okay.
The problem is that I was downloading it from your GitHub. Let me see if okay, I was here, and I've seen that in the MVLEM 3D, there is the TUB files.
Right.
While in the SFI, it is not. So basically what I did, but just because I didn't have time, I downloaded this one, and from the TCOL file, I took the information because I didn't have time to go through the papers, and I tried to change it for the SFI. Now, of course, it is not perfect because I didn't have time to change everything. I didn't have the information for the other configuration. So if you have your TCL files for the SFI, if you can send it to me the next day, I will complete the example and I will share it also. It would be nice.
There's one. I mean, there's lots of details here, but one important thing is if you scroll down a little bit.
In the SFI.
Yeah, just to that picture down there. So I'm sure people who used this model are aware of this, that this fixed strut angle model, the FSAM, currently can only be used with concrete CM.
Yes.
And that creates a little bit of a limitation in terms of computational stability, I would say. And we have a version of this model that works with concrete O2. And I've been saying this for now a while, that I'm going to make it available. I will. It's just so many things going on all the time. But this is one of my things on my list, because I think once we put that out there, this model will be much more stable and much easier to use, and will be converged much better too. And again, the problem really comes more from concrete CM material, because it's very complicated concrete material, than from the actual model formulation. So I promise I'll do it. I'm just not sure exactly when. I have so many things that I want to implement in OpenSees, and I'm doing one thing at a time. So, so that's the thing that the reason I didn't put the example there is because the one that I used for my paper publications and stuff is with concrete O2, and then it's not going to work for everyone. As soon as I implement all these things, I'm going to make everything available. So
okay, that's fine. Actually, yes, I was not using the TCOL file to run them, just to take the input parameters to create the model, just not to go through the papers, otherwise it will take a lot of time. But it's fine. I mean, I can go through the papers because you've sent the papers here, and yes. Okay, so let's start by with the tools that we have today. So you will see a folder called 04 SFI-MVLEM. Now, in all this example, I will show the implementation of the SFI, and I will show you also the MVLEM, but basically they are pretty much the same, except from an STKO point of view. They're not so much different. Okay, so as I said, the first one was the same wall we were using for all the other webinars, which is the Mastianek squat wall. And so we can open it. Now, due to the plane assumption here, you will see, okay, let me close the grid. Now we are always on the XY plane. You have seen this model also with the shell approach and all the others approach. Okay, so it's a simple, as a geometry, it's very simple. It's a simple connected series of faces. Okay, this one in the middle will be with the SFI-MVLEM. The others on top are shell elements. But actually, you can also get rid of them and create a rigid connection. I just wanted to model the actual stiffness of the top wall, of the top beam, sorry. Okay, so pretty much is the same. I was using the same steel model I was using for the others, which is the aesthetic material, but you can use any other. As Professor Kristijan said, for the FSAM model, we need in the current implementation, we need the concrete CM. So I tried to calibrate these material parameters to match the material properties we were using for the other models. Okay, so it has a nice aesthetic loop. So probably this creates an extra computational effort, but it is fine. Then once you have the steel models, well, this one will go into the web wall. This one will go into the boundary section, because actually here at the sides we have fiber beams. But correct me if I'm wrong, Kristijan, probably I didn't really need to model the flange beam, because actually I can assign also different properties in one of the fibers of the wall, right?
That's
so
correct. You can assign different thicknesses in the different fibers. Yeah.
So in this case, I proceeded in this way to match the same modeling technique we were using on the other models, but I will show you actually how you can do it the other way. So basically, we have this shell approach here. So the space in the middle will be the MVLEM, the top will be the shell, and on the edges you can assign any beam property, and it will be a beam column elements. Otherwise, there is another approach, okay, and I will show it to you. So as regarding the SFI-MVLEM, you need to define first, well, of course, the steel model, the concrete model. Once again, in this version, it should be the concrete CM. And then you create these ND models. It should be under material and the other ND material. Let me see, FSAM, okay? Once you're here, you can put the, well, as usual, for any of these things, we try to stick to the OpenSees formulation as much as we can. As you can see here, they're the same parameters. Once again, you have the link to the OpenSees documentation. So here, what you have? Here you have the tag of the material, of the steel material in the X direction, in the Y direction. In this case, they are the same. Then you have the tag for concrete. Then you have the reinforcing ratio in the horizontal and vertical direction. In this case, they are equal because in both directions we have 6 diameter rebar at a spacing of 180. So you simply have to calculate what is the area of steel over the area of concrete here, and you get this ratio. And then you have these two parameters. Actually, here I wanted to ask you something because I'm not really sure about them here. When you talk about concrete friction, you talk about the internal friction of concrete, right? So pretty much tangent of 32. It's
like a friction coefficient. Yeah, you 0.8, 1 is fine. Usually, I think I use 1 or 0.8. I mean, you don't want to go too low. Yeah, sorry. You don't want to have too small of a friction coefficient because then you will have a lot of sliding. In my dissertation, we have sensitivity that shows how results change. But I mean, you know, we tend these days to just take a lot of things for granted, but there's a lot of details here. So whoever wants to use this model, I really, you know, encourage you guys to really read the papers first and understand the theory.
Sure. And then we have the alpha down here. This is a stiffness coefficient for the double action. Once again, here I didn't have time to go through all the papers, so I tried to use.
I reckon this is a good number to use. Yes.
Yeah, I've seen some of the examples, but once again, now I will show you the implementation as a user in STKO. But to understand better the models, as Kristijan said, go through the papers and read about them. Okay, so once you have this, you have your three-dimensional model. It is a plane stress model, so if you want, you can test it inside STKO. Like, for example, I want to do a cyclic test in the X direction, okay, and I want to fix the stresses in the other direction to 0, okay. So this is what happens in the X direction. I want to push it a little bit more in tension, probably, so you will see the effect of steel, because as he said, now here you have, this is not only concrete, it's concrete plus this portion of steel. Is not that much, of course, because there is very few rebars, but you can see the modification it has. So it is a macroscopic material here. If you want, you can test it in the other direction. You can test it in shear. You just need to change. For example, here I want to test it in shear. I want to keep the other two stresses at 0. And you can put, I don't know, some numbers here. Okay, so you can do some tests to understand how it works. Okay, so this is very useful to understand if your parameters are correct or not. You can use the material tester.
Yeah, this is great. I like that. This is really, really useful. Yeah. And
then of course, here to match the modeling technique I was using for the other models, I modeled the boundary elements as beam column elements. So here you will find another concrete with the same parameters that I use in the CM. At least they match the same type of concrete. And then this concrete plus the 12 diameter rebars, they go into the fiber section here. Okay, and the fiber section will be assigned to the side boundaries. Now, I just realized that it's not completely necessary, because when you will need to assign an element here into this shell surface, actually here, You can go on the elements, you can find it under. Yeah, actually here we decided to put them under beam elements because when we started with the two-dimensional elements, we put them inside beam elements because actually they look like beam elements.
Yeah.
Actually, the 3D ones instead they are like surfaces, but for to be consistent with the two-dimensional one, we put them inside the same folder, so beam column elements. But you can find them here. So you have the MVLEM and the 3D one, SFI and the 3D one. Okay. So as Kristijan said, this is made of several parallel fibers that you have through the length of the element, so you can pick the number of fibers. These two vectors will be adjusted accordingly, because if I put 10 here, it will be 10 here. If I put another number here, they will shrink as well. Okay, let me open it again. Okay, so here I decided to have, once again, okay, so here you have the number of fibers. Then according to this number, you have three vectors. One for the out-of-plane thicknesses, which in this case now, since I tried to model only the inside of the wall, they are only equal to 100 millimeter. But actually what I could have done was to add 2 extra layers or few more with a higher thickness, which is, for example, 200 for these side boundaries. Okay, so this is why you can edit all of them. It is not necessary that they have the same value and the same materials. Okay. Then for the widths, also here, but one thing that is important is that the sum of them should be equal to the total width of the wall. Otherwise, you will have an error also in OpenSees. In this case, they are equal, which is basically the total length of the wall divided by 10. But if you want, you can extend it and you can include the width of the two beams, okay, on the edges. And inside there will be the total width of the wall. Okay, so actually you can play using different material parameters. And then of course the material tags. Once again, here I have 10 material tags all made of the same FSAM, which is the FSAM for the web. But if you don't want to model the side elements as beams, you want to model them as SFI-MVLEM, it's fine. You simply need to define another FSAM, because now of course you will have a different reinforcing ratio. Okay, so you compute the reinforcing ratio for the vertical direction, horizontal direction for the beams, and you can put a different layer here. Okay, so different material. So that's why you need this vector. Okay, both to integrate response along the thickness, but you can use different material parameters. And then of course, as usual in STKO, whenever you have optional parameter in OpenSees, here it is represented as a Boolean. So if you want to specify the optional parameters of, for example, the center of rotation, you can switch it on, and then you can update the default value if you want. Okay, so as you can see, the parameters are the same. The link should go actually to the new OpenSees documentation. Okay, so once you have done with your element, you simply drag and drop onto the surface. In fact, this one is assigned just to this surface. Okay, once you're done with this, all the other boundary conditions are the same for the work we have done in the other elements. So we have a fixity at the base, only in the in-plane direction. Then we fix everything in the out-of-plane direction. Then we have the self-weight for the web, which is a phase force, the self-weight of concrete, self-weight of the top beam, and then we have the self-weight as an edge force for the side beams, and then we have the pushover load here, which is actually an imposed displacement, unitary, because actually I will control its magnitude with either a monotonic time series, which has a total multiplier of 28, because 28 is the total millimeters that I want to push this wall, or through a cyclic if you want to do the second test. Okay. Well, once we are done with this, there are the recorders. Actually, there are many things that we can record in this element, but here we show only a couple of them, and then I will show all the others in the other example. Actually, I loaded all the results that we can have from this element. Okay. So as usual, you have a recorder. In this case, I just want displacement and reaction, and then I want a couple of things for the MVLEM. Now, the results name for the MVLEM are not listed within the standard ones, because as you know, element results in OpenSees can be theoretically infinite, because every element can have its own results. Okay, so here under the built-in results, we have only few of them, probably the standard ones like material stress, material strain, section fiber stress for the beams and so on. But if you want something custom, you can also go here and you can type your own, the thing that you want. For example, I know that in the SFI-MVLEM, I can ask a result, which is called panel stress on each material point. And this one actually, Kristijan, is one of the modifications that I've done, so I can show it to you. Just a couple of modifications that I've done in the SFI is, for example, here, where you want a material output, that you have to specify RC panel. I just added also the material keyword to make it consistent with the other, with the others. Okay. So
Yeah,
it's just that, and then many other modifications that I've done, which are not a huge problem, are these. The material tag for the XML. Okay.
Ay, sí. Todavía me faltan unos 5 días más que dijeron que tengo que...
Can you just a second? I will mute. Okay, I think it's muted. Yeah, the other main modification that I've done was to add all the XML tags. Then I will explain you why, but basically, you know that in OpenSees you can add, it is not mandatory, but you can add all these tags saying, for example, if you're asking for a material number, a material result, I can open a tag called Gauss point, then I can put a number, I can put the location. It's not necessary, but it's very useful for the MPCO recorder to understand how these results, what these results mean, basically. It's a sort of metadata, and we use it to recreate the data in post-processing. Like with these things here, I know each Gauss point, where it's located, and what is the thickness of the Gauss point, for example. Okay, so stuff like that. It didn't change anything special, actually.
Yeah, that's actually useful. I mean, I had my own ways of doing that, but
yeah, I decided to. Yeah, of course. Then there are plenty of ways for doing that.
Yeah.
And here there is another results that I added. I contacted you on email about this, which is the panel crack. You will see on the pull request what it is, but it will be in the FSAM. So also in the FSAM, what I've done is to add all this bunch of tags to say what are the components. Okay, so open a tag for the ND type of material and components and so on. The only results that I added to the FSAM is this one here, the panel crack. My idea was to do something like this. I wanted to have a tensor that describes the crack pattern in such a way that I can show with the vector plot. Similarly, when you visualize the strain and stresses field with the with the tensor representation, I wanted to do the same for the crack. So basically, what I did was something like this. So imagine that I have, this is my element. I imagine the angles are from the local x-axis, right? So this one is the x-axis of the element. If I have a crack like this, then I have the normal to the crack here, and then this one should be my angle for the crack, right?
If I remember correctly, yes.
What I did basically is to get the tangent vector of the crack, because actually I want to visualize the cracks, and the length of the vector will be proportional to the opening of the crack. So basically, what I wanted to create is to create a tensor which has basically two eigenvalues. The eigenvalues are the opening of the crack, and the eigenvectors are the crack tangent vectors. So basically, for example, there will be the opening 1 of crack 1 times tangent vector 1, dyadic product tangent vector 1, plus the same thing for the crack number 2, okay? Which is what you have here.
So are you also plotting like the crack width on the...
That's why I contacted you on email. So basically what I did was, first I get this Boolean value, and I initialize this vector. Actually, it is a tensor in point notation, but I initialize this tensor to 0. Then if the first crack is open, I add its contribution, okay, which will be the tensor product times this eigenvector, which will be C strain stress concrete 1, right? So it should be the strain of the first strut here.
Yeah, yeah.
Same thing. If crack B is open, I do the same. I take the tangent vector from the crack angles of the second crack, and then I multiply it by the material pointed for concrete number 2. Okay. Then here it is inverted because I want to take, since this angle is for the normal, I want to take the orthogonal vector. That's why it is inverted. Then I will show it to you. If they look fine, I will actually do a pull request like this. But basically, at the end of the day, here you have a tensor which has 2 eigenvalues. This one will be the first eigenvalue. This one will be the second eigenvalue. And this one will be the associated eigenvector, which is the tangent to the crack vector. Okay, so let's go back to STKO. If I run the, oh, of course, the mesh. So you have to take care of the mesh now. I don't know if you told that it is not mandatory, but actually it's useless to discretize the model in this direction, right? So it is fine to have only one discretization along the width.
Yeah. You don't need to have more because it's going to be plane sections no matter what. Yeah.
Exactly. So the only thing you need to do is to discretize the mesh on the height in this case. Okay. So once you've done that, you can run the analysis. What I've done here is to create a plot for the impulse displacement here versus the base reaction. So we can run it. It will take less than 1 minute actually. So, and even if this element is not made for this kind of application, this one is it's quite good for even this application. Probably I think I can change some parameters because here I was getting a sliding at the base, but I think it's normal because I don't. Do you think I can get the full diagonal crack with this element?
Yeah, I think so. But again, it's not the example is really not the best for this type. Yeah, I'm not sure if you can like. I guess you don't have test data, right? The dotted lines is test results.
The test data, yeah.
Yeah. So it's not ideal example. This model is more for like a medium rise to like slender wall. So
in any case, just to give a description of this, the fact that here it is a little bit stiffer, it's pretty normal because it's the same that we had for all the other examples. It's just here you have a lot of cycles at the beginning, and here I'm just doing a monotonic stuff here. So it's pretty normal that here I don't have this progressive loss of initial speed.
Yeah.
Just slightly estimated, but
these squat walls, they can have a lot of other like type of different like strain penetration. There's all sorts of other issues that you have to model to get them a little bit better. So this is, as you said, I'm expecting that other models have the same problem with the initial stiffness.
Exactly.
So yeah.
In any case, just with a simple, as I said, with a simple calibration like this, you can get reasonable results. But as I said, now in this case, it's not to. I don't want to waste time in calibrating the parameters. I just want to show you the implementation from a user interface point of view. Okay.
Sure.
So here you can go in post-processing. Let's open it. So by default, of course, you will start with a surface color map. By default, you see the deformation. Here in this case, I predicted a sort of sliding, but all the other models were predicting a diagonal crack here. But with a coarse discretization, also they were predicting a sliding here. So this is pretty fine.
Yeah, you could, maybe the friction coefficient and things like that can be calibrated to get a little bit.
Yeah, sure.
Yeah.
So as I said, I didn't spend time understanding the element and calibrating.
Yeah,
so
of course. No, this is fine. I mean, so can you, I'm curious to see like those stresses and principles.
Exactly. So for example, the first thing that you can do is to use, if you use surface maps, okay, like this one, you can still access results on the Gauss points. Now, panel crack is not necessary to visualize here, but for example, if you want to visualize the strains, you can do it, but it will be a linear interpolation between the first Gauss point and the last Gauss point. Why? Well, because in any software, basically, when you have internal Gauss points, you do a nodal extrapolation. So from the Gauss point to the nodes. And so basically you have, imagine here, you have several Gauss points. I have the first one here, and then I do a linear interpolation to the last one. In FISTA, same thing for, well, of course, here you have the strains. So in STKO, we get the 3 results that we have from OpenSees, and then we compute the eigenvalues, principal max, and then some of the typical invariants. Same thing for the stress. Okay. Now, if instead you want to go into the details, you are not fine with a linear interpolation. Okay. I don't know why I'm visualizing the pressure, but probably this one is what we need here. If you don't want to visualize just the linear interpolation of them, you can go with a Gauss plot. With a Gauss plot, what you can see is actually all the integration point in their location. Let me go back to orthogonal view. Okay, so it's easier to visualize. If you remember, you can start by a constant and you will see all of them with the same size but just different color, or you can adjust the size to have the minimum size at 0, so you can see by intensity where are the higher values. This one, for example, is the stresses on the, no, this is the panel crack, sorry. If I go to stress here, you will see like the beginning, you have the stresses here, then you have the opening of the crack at the base. So this is the stress in the orthogonal direction. And then here already you can see, for example, the diminishing stress here is basically the crack tip that goes through the other side. Okay. Then if you want to visualize any tensor, you can do it, as I said, with the vector plot. Okay. So with the vector plot, you can visualize both vector results or tensorial results. Okay. Now, of course, this is the displacement. Oh, a side thing now that I'm here, you may experience something strange with this element. In fact, I wanted to ask you something. For example, now by default, I created a vector plot, and by default, I'm picking the first result, which is the displacement. As you can see now, you can see the vectors here. So what do they are? Well, if I show nodes, you will see that actually this element adds some internal nodes, which are not added by the user. They are added inside OpenSees. So in the output, you see them. Now, there is a way to get rid of them. Like if I don't want to see them, I can go here. I can select, I don't know, I want to visualize only the results for the MVLEM. I can isolate it and then I get rid of those nodes. But I was just curious to understand what they are. I've seen that they are a single degree of freedom nodes, right?
Right, right.
And they have.
Okay, I'm gonna try to explain this in a simple way, I guess. But there's no really simple way to explain it. So basically, let me then share my slide because I should have that somewhere over here.
I stopped sharing my screen. Okay.
It's related to the model formulation, and it's let me just see if I can find a good slide for that.
Yeah, I've seen in one of the latest slides that there were those small deltas.
Actually, none of my slides are showing that, just the one that I showed here. Hold on 1 second. I'm just going to open one of the papers and maybe the best will be to open the very first one. Okay, so this is what it is really. When we put this fixed strut angle or whatever, you know, plane stress element at each of the fibers, right? You have vertical strains, epsilon y, you have shear strains, and you have epsilon x, right? So you have this extension strain. like this. So as you can see in this picture over here, from these 6 degrees of freedom, 1, 2, 3, 4, 5, 6, you can calculate epsilon y because you know how much every fiber is extending. You can calculate gamma xy because you can calculate the shear deformation, but these degrees of freedom over here are not related to the epsilon x. In other words, each of these fibers has ability to kind of breathe horizontally. And now these degrees of freedom are in fact part of the global stiffness and force matrix of this vector. So when the element is doing its solution strategy, it has to converge not only on these degrees of freedom, top and bottom, but also at all these horizontal ones. So the actual number of degrees of freedom in this element is not 6, it's 6 plus n.
Yeah.
So the reason we have these 1 DOF nodes is because they have to reach equilibrium with everything else in order for element to converge. They're part of the element formulation. So at the time, I guess that was a long time ago now, this is how I implemented this. I had to add a node there with a 1 degree of freedom.
Okay, I get it. So basically they are the horizontal expansion basically of the
horizontal expansion. Yeah, they don't necessarily have a direction because they're associated with, conceptually, and they represent horizontal expansion, but in OpenSees it's just 1 DOF. It doesn't really have,
And is there a constraint between them, like the overall expansion should be equal to the, because in this case you have the lateral nodes of the elements, so you can actually calculate the overall expansion of the element. Is there any constraint between them, between their integral and the total expansion of the pod element, or there is no relation?
The element actually cannot expand because it's just like a fixed, it's a rigid beams and it's a macro element. So it doesn't have that ability. So, but each of these fibers, they can expand and they can, have horizontal strains. As you can see here, the assumption is that the stress at these faces is equal to 0, right? The sigma x in each of the fibers is 0. And that's from that condition, we're actually getting that strain at each time step.
Okay.
And this is exactly the reason why this element cannot be used for very squat walls, is because of this assumption, because for squat walls, this assumption is not very good. For medium rise and for slender, it is. So in the element that we're currently working on for squat walls, we actually improved this assumption. And that's the whole catch, really.
Okay, I got it. No, very clear. Thank you.
Okay, great. So these are macro models, and then for users who are here, like macro models are like that. You have some simplifying assumptions. They are computationally efficient, but they have these limitations. So you have to have different versions of these models to work for different things.
Yeah, sure. In fact, one thing that we have said, but also with the more detailed models, there is not a unique model that can work for every kind of situation. So it's useful to have the knowledge of all the elements that you have in OpenSees, so you can pick the best one for the situation you're analyzing. So just to remind you, if you see these nodes here, whenever you load the results from the SFI-MVLEM, don't worry, they are not. It's not a mistake you did. They are not coming from this element. Okay. So if you see them, don't worry. So I was instead explaining the tensor that you can visualize. So you can visualize as usual the strains here. Okay. Also here for any kind of glyph representation in STKO, you can both have constant size, and so you can see the directions of the strains in this case, and only the color depends on the value. But I prefer actually to scale the size with the value, so that you can see where is the major value. So in this case, if we have deformation, we have a sliding here, so it makes sense that we have a lot of deformation here. If we try to look at the stresses, okay, you can see how here the stresses are much lower because there are the cracks here developing. Okay, so it makes perfectly sense. Okay, like this. And then if you want to visualize the crack instead, we can see this result. So panel crack. Once again, let's start with the constant size. And here I don't really want colors, I want a constant color. So if I start from the very beginning, and let me probably put a little bit smaller. Okay, so what I'm visualizing here is if the size is constant, is basically I'm visualizing if a crack is there or not. Okay, so in this case, I have one single crack in each direction, inclining in this direction. So here that's like a standard tensile crack. Okay, and then when it reaches here, you have major shear deformation here. Okay, so here you have only one crack per side, but this makes sense because it is monotonic. Then in some cases, up to the end, you see a couple of cracks here. If you want to scale them with the size, you can go here and say, okay, mean size at 0. So you can also see where is the crack that is opening more. Okay. I also want to show you all the other results that you can visualize, but I wanted to pick a better example. So what I did actually was to go here in the GitHub. As I said, I wanted to download the example for the SFI. It was not here. So what I did, I downloaded the example from the MVLEM, the TUB. I tried to change it, but as I said, I will update it. If Kristijan, if you can send the TCOL to me, it will be easier for me to calibrate it. Even if it is a concrete 02, I will convert it to CM. Yeah. Otherwise, I will go through the paper and I will try to adjust it. But
yeah, I can do that. Just please send me an email and I will send you the model. Yeah.
Okay, actually, just to speed up the updating of this one. So if you go inside of the second folder, you will find that example. As I said, I plainly look at the TCOL file and I rebuilt everything here. Okay. So just a brief explanation of what you have here. You have your shell for the MVLEM element. Then you have a compound of things up here, which are rigid beams.
Yeah, we use them just to apply the gravity load, and we didn't have to use these rigid beams at the top, but at the moment, I think the student who worked on this decided to do it that way. It doesn't impact anything really. And then this little pink or purple is there just, we need those 2 points at the end that are sticking out because that's where the test result, that's where they were measuring the displacement. So we wanted to be precise. So they're just kind of going for the ride. They're just to get those 2 points. Yeah,
that's fine. I mean, you can use either rigid stuff like this or rigid links, but yeah, sometimes I also use rigid elements because making too many multiple constraints can be tricky. But yeah, I understood actually what they were. What I didn't understand actually was the link here, because actually we have these 3 points. If I select them, you will see them. 1 point here, which corresponds to node 51 in your model, node 23, node 25. Right. They are the loading points. I just didn't understand these links with a fixed node. Is it to record reactions or?
No, so if you look at the test, how the test was performed, it was actually, as I already mentioned in my presentation, it was pushed laterally, but it was also restrained against twisting.
Okay. It was to avoid the torsion. Okay.
Yeah, because the tricky thing is that when you have a section like this that's not torsionally symmetric, if you push it horizontally, it's going to start twisting, right? So you have to find a way to apply all this complex loading history and to prevent twisting. Now, one way would be to push it in this direction and then constrain it, then let the constraints go, push it, but that is not going to work. So we decided to go with this approach where we basically have these elastic springs with a very high stiffness at the locations where the actuators were. And then we are pushing against those springs with a very high forces. So when I'm pushing in perpendicular direction to the spring, because the spring is so stiff, it's holding the specimen against twisting. But when I'm pushing against the spring, then then the other guy is holding against twisting. So it's really to apply the load correctly and to impose the correct boundary conditions. And that's the challenge that I mentioned earlier. It was kind of tough to actually do this because you have this complex loading history, and you have to prevent twisting, and you have to push the specimen in all these different directions. And I think you're maybe missing one, and one needs to be in the I believe X direction, or maybe one of them is in the
probably no, yeah. I mean, I think it is drawn in this direction, but actually, let me double check it. Because we have it here, the one which is in the Y direction. Let me select them. After all, they are zero length. So this
okay, I see. Okay, yeah.
And this one should be, yeah, in the X direction. Yeah, I draw in the same direction, but actually it is a zero length, so it is not important the location. Yeah, but now,
in the paper we explain this a little bit more, why and how, and so it's a little complicated because again, it was a complex loading history and the complex boundary conditions.
I've seen also that. Yeah, I was seeing that it was very complicated. So I tried to put some vectors here, but as I said, I want to just to tell all the other people, I will upload this file just after I finished to set it up, because actually I did it blindly, so I need to talk a little bit on it. Once again, I started from the MVLEM. Okay, so then I converted that material model to a concrete, but then I didn't have time, so I created a single FSAM. What I need to do now is to create all the other FSAM, because actually there are different portions of the wall. I think here it's visible, here these different colors, they have different material thicknesses, different reinforcing ratio. So I need to set up all of that. But this is just to show people how they can do it. Okay, so we have all these boundary conditions. The only thing that I was looking into the file that was something like this. So there was a procedure to apply a certain couple of forces, and this was repeated a series of times, right?
Yes, and this is exactly this. So we're applying these forces for each loads. If you can go to the one of the web pages that I have with the loading protocol.
I think it was probably in the
other show actually here.
I've seen a drawing of this.
Let me just share my screen again real quick. I mean, this is now we're going really into details, and this is all related to this particular specimen. So I don't want anybody to think that you have to do it like this. This is just because this test was complicated. So for each of these lines, so basically, you know, from point 0 to A, then from A to G, from G to D, for example. So each of these, we had to apply a separate force control analysis. So we decided to do it that way because of the boundary conditions we applied and so forth, right? So the reason you're seeing all these, a list of different force control analysis, is because the loading is changing direction, right? You see first I'm pushing up and down, then I'm pushing left and right, then in fact I'm pushing this sweep like this. So each of the segments is a separate load of force control analysis. That's the reason we have so many different ones.
Again, yeah. Okay, so basically what I tried to do, but once again, I'm not sure if I did it correctly. I was attempting to do it in a single analysis. So I decided to, well, looking at this, basically I've seen that you were actually calling this one many times with different components. Then these components are phi x and phi y. Then I've seen, for example, in node 51, you always apply 0 of x and 0.5 of y. While node 25, you always apply 1% of y and 0.
Yeah, because in y direction we had 2 actuators, so I'm splitting half-half, and in the x direction we had only 1.
So basically, what I did, just to understand if it is a key, and then what I've seen is that actually these are increments of loads for that cycle, because actually before starting, you keep the load constant and you restart from 0, right?
Mm-hmm. Yeah.
Basically, at the first, just to understand, for example, the first step, you apply the load according to these two values, then you keep them constant and you add this one. So in this case, basically, you are going to minus this value and then you go to 0.
Yeah, then you push back to 0, then you push to the other side, and you push back to 0. Then
so basically, yeah, what I did was to extract those data. And here I simply did this one is this one plus the previous one and so on. So I took that.
Yeah, there's different ways to do it. So
Yeah,
Maybe
I just wanted to know if it was equivalent or not, because I was not so sure. So basically what I did is to get these two path vectors. This is path X, and this is path Y. And
something
then
like that. Yeah.
basically what I do is to apply two loads, like Fx, which is applied to only this one, 100% in the X direction, and Fy is applied on these two values with 0.5. And then basically what I do is to simply apply two load patterns, the Fx with the Px, the Fy with the Py. Okay, so these other stuff here. Then I was preparing some monitor. I prepared only one, but actually I need to update it. Then the total analysis, yes, also here I had to do something like 12,000 steps, which is pretty much the same number you have shown. So it is pretty fast. Actually, it was, I don't remember, but something, yeah, close to the value that you gave. Let me see. But actually, don't look at the result because, as I said, they are completely different. 20 minutes, but I only use the material for the core without any boundary elements. So they are completely wrong, the results. So that's perfect. It was just for visualizing.
Maybe like for the purpose of this example, you can just simplify it, remove all these weird things and just push the wall in one direction, push it in, just as an example. I don't want people to get confused because this was a very complicated experiment to begin with. We're pushing it in all these directions. And if you just want to see how to model a wall with this element, maybe just a simple pushover will be, you know, less confusing or something. I'm not sure where people are right now with.
Yeah, probably yes, because otherwise they will be confused about more about the condition rather than on the wall itself. Also here you can go on post-processing. Oh, and once the other thing that I wanted to show you in this example, you will see that the output is quite heavy here because I decided to put here all the possible results available with this element. Now, as usual in OpenSees, the results are very complicated for users because they typically lack documentation and people do not know what they mean. So we can take advantage of this webinar just to explain something, but there are some results at the global level, and then you have all of them with the material dot something. They are the results at each integration point. So panel strain, panel stress, correct me if I'm wrong, they are the total homogenized.
Yeah, the epsilon xy gamma xy and the sigma xy tau.
They contain both the components from concrete and steel. So the overall.
Correct. Yes. And then we have steel in x and y directions, basically strain stress. So you would have the strains and stresses. So you know, in both directions.
And only the concrete, the 3D stress, the concrete. Then you have.
And then we have concrete strain stress along each of the struts. You know, have two perpendicular struts, so you have concrete strain stress in each direction. You have the interlock response, basically that friction coefficient that we're using. There's a little friction mechanism along the cracks, so you can plot that, and then cracking angles.
Yeah, cracking angles, which was the default result you had for cracking angles. Then we have this extra result, which is panel crack, which is instead useful in STKO, basically.
Yeah.
It's the same meaning of cracking angles, but as a tensor, so that you can directly visualize it as with the vector plot. Then there is an extra result to get input parameters, but I don't think it's useful for the user because it's to get the input parameters that she gave, right? So probably it's just for debug, I think.
Yes, and there's, I think, in the meantime, I discovered a better way to do that. So I'm gonna probably remove that eventually, but
probably it's the parameter. Yeah, there is the parameter stuff.
Yeah.
So in any case, here you have the entire list. So you can use this example to remember what are all the results, and you can visualize all of them. As I said, they are results on Gauss points, so you can both visualize them here. Like I want to visualize, for example, the panel stresses. You can visualize both of them either here, or as you can see, for example, sigma 1 is almost 0 everywhere. It was because of what Kristijan was saying before. So it's the horizontal stress which is imposed to be 0. Okay. This one instead is the vertical stress. Okay. So you have positive stress and negative stresses here. We can adjust deformation scale. You can do some animation here, so you can play with it to see how it works. Once again, if you want to go into the details, so if you don't want just a visual color map, you need to go onto the Gauss point plot, and you can look at the things that you want, like panel strain. You can look at the strains that are developing all here around the wall, or well, you can look at all the other results like stress, strain here, or the stress interlock. Well, there are a lot of them, so you can play with them and try to see what they mean. And finally, also here, you can go down onto the vector plot, and you can choose, for example, the panel crack. Okay, so here for the panel crack, I want to show this one. Let's start with a small value, constant, so you can see all the cracks that forms. So from the beginning, so in this case, you will see only if a crack has formed, like start with a simple animation. Okay, here then the other, probably a little bit of deformation is also necessary. But here in this case, you don't have information about how much they are open or which one of them are reclosing. So if you want to see that, you can use the mean size at 0, and probably you can increase a little bit crack size. Okay, so here you can see the crack as they are developing. Do it looks correct to you, Kristijan, at least to visualize them like this?
So this the arrows represent the directions perpendicular to the crack, or the actual crack itself?
No, this one should represent the actual crack. Okay.
Okay.
The
So
actual
first
crack,
of all, yeah. Okay. Yeah.
and their length is scaled with the opening. So the longer they are, the more open they are. If instead you want to keep their length constant and you want just to rely on the color, you can keep constant, go to 0.5, for example, and you can change the color. For example, I want only to see, I don't know, the blue ones should be the minimum, and then they go to the red.
Right. No, it looks, I mean, you know, if we push the wall to the left, crack is going to open like that. One thing maybe a little bit confusing to me are the arrows at the end, because it makes me think that something's happening in that direction. I'm not sure if you can eventually not have the actual arrows, but just like a line.
This is exactly what I was thinking, because actually, yeah, this is used to distinguish between positive and negative values, but for the crack, it doesn't make sense. Actually, one thing that I was noticing is that with that operation that I made, some of them are negative, but actually they should always be positive. So, or actually, I don't know. I mean, here, for example, I multiply them. It always happens with the second crack catch. Well, I don't know if it is only on the second crack, one of them anyway. But does it make sense if one of them can be negative, like strain stress concrete, one of them could be negative according to you?
I think so, yeah. I mean,
so because for example, if I close one of them, yeah, some of them can be negative, like here, or probably it's just a numerical stuff. Anyway, probably what I will do is to have the opportunity to have a vector plot, you know, in STKO, which is dedicated for cracks,
right? Which
does not have the end arrows, so it's just a direction. And probably in that way, what I can do is instead of scaling the length, I can scale the thickness of the line.
Thickness, exactly, that's what I was gonna say. And then it will look like an actual crack. Yeah.
Exactly. So what I do, for example, if this crack is more open, I can do a thicker line here and a thinner line here to understand that one is more open than the other. Because,
I think that would be great. Yeah.
Length gives you an idea, but it can also get confusing, because when you are here, it gives you an idea of what is opening and what is not, but probably it's better if the thickness changes. Yeah,
I think that would be visually, that would be like more realistic, I think.
Yeah. Okay, so that's all for today's webinar. As I said, I will share these files in a couple of days. I just need to finish setting up this one, and I will share instead a simplified version of this, because probably all this assembly up here is way too complicated to understand. So we'll simply apply a pushover, simply monotonic load in one direction.
Yeah,
okay, so
both files available, but for the beginning, it would be nice to have a simple one so users can,
Sure. So thank you, everyone. I don't know if you have a couple of questions now, but I want to remind you that the 8th of September, there will be the final day for this webinar, where will be dedicated for question and answer and a round table. So if you have complex questions, you can ask them directly on the 9th of September. In the meantime, if you have some question for Professor Kolozvari or for me, we are here for another couple of minutes. So thank you, everyone. Thank you for being here. Thank you, Professor Kristijan Kolozvari, for participating to this webinar, and thank you for your presentation. So let's see if we have some questions. Let me go back to the chat. Okay, I don't see question in the chat. Everyone. Okay. So if there are no questions, as I said, no worry, because there will be one day dedicated to question and answers. So thank you, everyone, for being here, and thank you to Professor Kolozvari for participating to this webinar.
Thank you for the invitation.
Kristijan, thank you very much also from me. Thank you.
Thank you. Bye-bye.
Bye.
Everyone, thank you, and see you the 9th of September.